questions before we get started? Any questions for you, sir? I hope everybody had a great spring break. I'm gonna start off here, kind of recapping, an example or two that we kind of finished with, so many years ago before the break overtook us. So let's look at Z36 first. The question I want to answer here is, what are the zero divisors, what are the units, and what are the nilpotents here? Zero divisors. Anybody got a stab at any of these? The nilpotents might be the easiest to type first, perhaps. Somebody remind me what it means to be nilpotent. Yes.
So the one where if it's raised to some power and it equals zero,
Right.
it's no bonus.
So what is it gonna take to raise one of these to a power and get zero, right? Ooh, I bet zero works, right? There's that, right? But think about this as an integer, right? For this thing to be zero, you have to have a power of it being divisible by 36. Everybody agree with that?
Yeah.
So can you think of,
Just six.
okay,
And six.
or any multiple thereof, right? Because if you've got a 2 in you and you've got a 3 in you, like 6 does, when you take a big enough power, you're gonna have a power of 36. And actually, you're gonna need both of those, right? Because 15's never gonna work, because it's got a 3 in it, but never a 2. So no matter how big of a power I take this, it's never gonna be equal to 36, right? Same problem with 4, right? It's got the 2 in it, but not the 3. No matter what power I take of this, it's never gonna be divisible by 36. Everybody agree with that? So the nilpotents here are all the multiples of 6. Uh, 4. That. It's called. Okay. How about the units? I characterize the units. That is right. Units are everything that is relatively prime. Well, let me kind of prove this. Suppose you have some number, right? This can be a general number, not just my list of 36. Suppose it's relatively prime to 36. That is the greatest common divisor of these is 1, right? What's a big thing that we had early on in the early thing? There's a linear combination of n and 36 that gives you 1. Everybody agree with that? So there exists x and y and z such that nx plus 36y is equal to 1. Everybody agree with it? So this means whatever n was, reduce it mod 36, divide it by 36 and take the remainder, and it will be one of the numbers over here. Everybody agree with that? And in fact, n bar times x bar is equal to 1 bar. Right? Because that 36 is a big fat 0 here. Right? So any element that is relatively prime, the 36, so to speak, has this power. So this is 1 bar, 5 bar, this might be kind of obnoxious, 7 bar, 11 bar, 13 bar, 17 bar, 19 bar, 23 bar, 25 bar, 29 bar, and 31 bar, 35 bar. And actually, the number of these things can be told to you by the old Euler phi function. Everything else. All zero divisors, because what happens with everything else is it's either gonna have a factor of 2 in it, or it's gonna have a factor of 3 in it, right? If it's got a factor of 2 and a factor of 3 in it, it's in this list. Right, so in other words, all the zero divisors, let me, instead of saying all else, all non-units. Let me be clear about that, because these nilpotents are all zero divisors. So this should be a subset of all the zero divisors. But the zero divisors are ones that have a factor in common with 36, right? And that's what makes them a zero divisor, because, for example, 2 bar times 18 bar gives you 0, right? 9 bar times 4 bar gives you 0, and so forth, right? And the key there is it's got a factor in common with 36. Are you okay with that? Yes.
Briefly redefine unit.
A unit just means it's invertible in the sense that it's got an inverse, and namely, the inverse of n bar is x bar, because 1 bar is the identity. How about this? How about the 2 by 2 matrices over 3 of us? This one's a little bit, can we identify zero divisors here, nilpotents here? Suppose I take the ring of 2 by 2 matrices overall. Here, the multiplicative identity is the identity matrix, right? 1, 0, 0. Anybody? Yes,
You said units are worth us the inverse, right?
that's right.
So it would be non-zero determinants.
There you go. Here, the units are the invertible matrices. And there's an easy way to characterize it. Non-zero determinant. Okay.
Yeah, so is that way of thinking about units always okay, or is there any time where let's just think about the fact that there's an inverse, is that ever like?
That's right. It has to be a two-sided inverse.
Two-sided,
Right.
okay. Yeah.
How about the zero divisors? Zero divisors are, so it looks to me like, look at this ring. It looks to me like if I walk up to you on the street and I give you a matrix, one of two things is going to be true. It's either going to be a unit or it's going to be a zero line. Right? See if you can prove this is true. You might want to guess what it takes to be nilpotent. Maybe I'll give you a hint, maybe it's straight down the road. Does anybody know what it means for a matrix to have zero determinant in terms of the eigenvalues? Oh, well, the horrible looks come over people's face for 30, right?
Are they not all unique?
A matrix, remember, the determinant of a matrix is the product of the eigenvalues.
Oh, so
Right.
it has zero eigenvalues.
So for a matrix to have determinant 0, it has to have at least one eigenvalue 0. Nilpotents are like zero divisors on steroids. Anybody want to guess what a characterization is from nilpotent matrices here?
Is it every eigenvalue is zero?
All given. This is some eigenvalues. So now, these examples are very illustrative, but they paint a deceptive picture. Let me give you one more example. The deceptive picture that they could paint here is in both of these examples, you had two things that happened. If I give you any element out of any of my two examples here, unit or zero divisor, that's it. Here's an example here. Let's just take the ordinary integers and see. No votes in the ordinary integers. 0 and 0 alone. What are the zero divisors? Same answer. Only 0, because in the integers, if a times b is 0, then one of a or b has to be 0. That means there are no non-zero zero divisors. And what are the units? What are the invertible elements of the integers? What's that mean?
Zero, but no, integers comes negatives. Is it invertible under
Multiplication.
multiplication? So. Zero.
No, zero's not invertible. Zero's only invertible under addition. How about yes?
So just everything other than zero? Aren't they complements or no?
I know what you're thinking that, but see, so let me rephrase the question. The inverse of an integer is the reciprocal. Everybody on board with that? Which integers have the property that their reciprocal is still an integer?
You said one and negative.
Now notice, this leaves a boatload of integers out of the picture. Everything else, in absolute value of n bigger than 1 is called a regular element. It is an element that is, well, sometimes regular elements include units, but I will call these regular here. They are the elements that, and most of the integers are what I call these regular elements, right? They're elements that are not zero divisors, and in fact are not units as well, in this case. Okay, any questions on it? Yes.
So this thing where everything's either a zero divisor or nilpotent, that's a special case. That's not always
That's a
true.
special case.
Okay.
And in fact, I want to give you a neat little theorem about that in a moment. Yeah, but that's, one does not expect this to happen in general. Okay, so. Sure. Oh. Theorem. Doesn't have to be. Then you are. I'm gonna use this notation to define the units for. This is the set of U and R such that U is a unit, which is the set of U and R such that there exists a V and R with UV equals V, U equals 1. So that's just a reminder of what a unit is. is a group. Right here. Oh. Okay, I'm gonna prove this real quickly, because why the heck not? Prove. Notice that one is a unit because its inverse is itself. So this is not empty. Well, it's not separate. So let's let U V be and U R. So there exists X, Y, and R such that UX equals XU is 1 and BY YB is 1. So that's what it means for those two to be units. Notice that UV times XY, whoops. Careful, that's negativity here. By the way, what should the inverse of UV be?
B inverse, U inverse.
Yeah, that's right. So let me write that way. In my notation, it's YX. Because Y is the inverse of V and U is the inverse of X. But what you said is this is U VY X, which is U1 X, which is UX, which is 1. And YX UV equals Y XU V, which is Y1V, which is YV. Therefore, full unit. So we're closed under multiplication. Let's see, what other obnoxious things do we have to worry about? Well, associativity. I'm just going to put a check there. Why can I be such a lazy man? Because we already know the ring multiplication is associative, correct? So there's nothing really to check here. Identity. That's just the one that I've already noticed, that I've already noted is in there. And inverses. By definition. Because what it means to even be a unit is it's got an inverse, right? So this forms a group. Let me give you another result, which I am not going to prove because it's in your homework, really. Suppose, so I'm going to state this carefully here. Let R be commutable. So we'll start off just with the assumption, not even that it's got an identity, and 1 if X, Y, and R are nilpotent. so is, uh, so are both, x plus y and x times y. By the way, and this is a homework problem for you. You do need commutativity here, and you also need nilpotent, because it's not necessarily true that the sum of two zero divisors is still a zero divisor. It's possible to add two zero divisors and get something that's not a zero divisor. On the other hand, if they're nilpotent, it's closed under addition. I guess that's an otherwise. Two, if R has identity and U is an element of the units, then U plus X is a unit. That is to say, if your ring also has an identity and U is a unit in the ring, when you add a unit in a nilpotent, it's a unit. Yeah. Both of these, or all of this, really depends on commutativity. Right. So this continue, yeah, it depends on commutativity. Okay, any questions on that? Questions so far? So, there's a special case here. One might consider these kind of the easiest rings of them all. Definition. What are the ring with identity? Such that R minus zero is a group under multiplication. We already know that everything in R under addition is a group. It's an abelian group under addition, right? Here's something special that can happen. Let's toss out zero because zero has no chance of having a multiplicative inverse, right? So we're going to toss zero out. If everything left over is actually a group under multiplication, we say R is a division ring. And I guess this name is suggestive, right? Because what it means is basically you can divide by everything that's not zero, because everything's a unit except for zero. A commutative division ring. So if order of multiplication doesn't matter, so in other words, this is not just a group, it's an abelian group, because order of multiplication doesn't matter, is called a field. And you all have seen examples of this, whether it's been pointed out or not. Let's look at some examples here. Started. Could somebody give me an example of the field? Okay, great example. Rational numbers, right? Because any, this is certainly a commutative ring with one, and if you have any non-zero rational number, it's invertible, right? Because as long as your numerator is not zero, you can just flip it upside down. There are bigger fields. Yes.
Oh, definitely. They're asking for more.
Yeah. So, This is the set of A plus B square root of 2, where A and B are rationals. You should verify for yourself that this is in fact a field, that it's closed under multiplication, division. Yes.
So when we're talking about the field itself, it can include zero.
Yes, the field, in fact, it has to.
Yeah.
But you've got to toss it out if you're going to talk about forming a multiplicative group, because no matter what, that zero is not going to be invertible. Reals, the complex numbers, these are all examples of fields that you probably encountered at some point in your travels. All these are infinite. You probably know what a finite field is.
C mod P.
Right. All positive primes, C mod is, right? The easy example is C mod 2, right? That's a group under an abelian group under addition. And if you jerk out the zero, you've just got one, right? So there you go. That's a group. So these are examples of field. Anybody know an example of field that's not C mod? Let me restate. Anybody know an example of field that's finite but also not C mod P? Yes.
Isn't it like an algebra group of field, or is that not a field? I can't.
It's not a field. That one's got zero divisors.
Oh, okay, gotcha.
I should say it's not generally a field. If you've
Okay.
just got one copy of Z2, it is a field, but if you've got multiple ones, it's not. There are actually other examples of fields you can see, but as it turns out, any finite field, if you have a field that's finite, has to have prime power order, right? P to some power. So you could, in theory, have a field of order 27 or 81 or 32. And in fact, you do for every one of those. And there's only one, but we'll talk about that later. Here's another one for you. Here's a brain scratcher. Does anybody know an example of a division ring that is not a field? All right, so like a field, only it's really not commutative.
Would all invertible matrices be one?
That's a good idea. Here's the problem with that though. That's not closed under addition because you can sometimes add invertible matrices and they're not anymore. How many of you, are there any physics junkies out there? How many of you have heard of the quaternions? A division ring, something. And the way you build this is this is the set of A plus BI plus CJ plus DK, where A, B, C, D are real numbers. And the IJK business is the quaternion group of order 8 that we had seen earlier. So you have I squared equals J squared, K squared equals -1, IJ equals K, JK equals I, KI equals J. And if you enforce these rules, you actually get a division ring, and it's not clear, it's not even clear this is associative. Go try to prove it's associative and then burn me an effigy for having asked you to do that, because it's a mess, but it is true. This is an example of a division ring field. Another example would be you can have rational functions over Q and two variables, but the variables don't commute. So this is called the ring and knock, this is called the, well, if you just have polynomials, we call it ring of two polynomial variables. Look at all fractions from this, and that's another example of a division ring that's not a field. We will mostly concentrate on kind of the nicer case here. Let me give you one more definition. Definition. Yes, it is. A commutative ring with identity. That's 11. Let R be a commutative ring with one. The with one is important here. I'm going to define a concept called integral domain, and there are two things always assumed by it. One of the things is it's got an identity, it's got a one, and that's sometimes skipped over. Don't forget that condition. R is all integral domain. And I'll put integral in a parenthesis because sometimes people suppress that and just say a domain. So if I ever say R is a domain, I mean it's an integral domain. If zero is the only zero divisor. So in other words, what it means to be an integral domain is R has one. It's got an identity, and A, B equals 0 implies A equals 0. So an integral domain is very fundamental because it allows you to do what you're used to be doing in like a more basic algebra course. Everybody loves to see A times B equals 0 means that one of these is 0. And this is fundamental things that you did back in high school algebra, even back when you were graphing and finding solutions, roots of polynomials and so forth. So an integral domain is the playground where you can actually do this. So let me give you a first kind of little baby observation. Let me give you an example of an integral domain. The ordinary integers, right? Here's a large class of integral domains, but it's far from complete. Any field is an integral domain. Let me point out the converse of the statement is certainly not true because, for example, the integers, the ordinary integers is an integral domain, which is not a field. However, if you are a field, you're an integral domain. So let's prove this. If F is a field, then certainly the non-zero elements field must form a group, so you have to have identity. So we've got that licked. Now suppose Z is a zero divisor and F. Okay, so let me be careful about what this means. This means there exists a non-zero A and F such that A, Z equals 0. Am I agree? That's what it means for C to be a zero divisor. You have to be able to find some non-zero thing. In this case, I'll call it A, such that A times Z is 0. But if A is a non-zero element of this field, what is true about it? What must it have? What is true about any non-zero element of a field? It must have a, that's good, it must have an inverse. Since A is not zero and F is a field, A inverse is in F. So let's multiply this equation by A inverse. What have I proved? I proved that if you have any zero divisor, it must be zero. But that's a domain because we proved that any zero divisor must be zero. Okay, any questions on? Let me make one more observation before I put this really groovy theorem. I'm gonna call it theorem cancellation. Theorem 9.113. This is kind of another observation about how rings that have no non-zero zero divisors are sexy, because we can do cool things here. Suppose ring with no non-zero zero divisors. Then if for A, B, C, and R, we have AB equals AC, then what are you just dying? If for A, B, C, and R, and A is not zero, what are you dying to do here? What would you love to do? Love to be able to cancel this, right? And the absence of non-zero zero divisors allows you to perform this. Notice suppose with A dot zero. Well, then bring AC over to the other side. And then factor out an A. Now, what do we have here? We have a product I didn't say anything about the ring being commutative. I do need a little bit of commutativity here in a very small way, because what I need is I need that there aren't any left zero divisors, right? So if zero is only left zero divisor, and well, actually, I guess right, because that would be zero divisor, and A is not zero. This implies B minus C must be zero. Therefore, B, C. And if I'm in the commutative case, I don't have to make any distinctions about that left and right there. So there's cancellation. Let me give you this. So here's a theorem. We're going to get a very famous corollary. I do this a little bit different than it's all the time. It's a standard book because I like this build-up result here. Um, but R, the a finite ring. If A is an R, then A is either a unit or a zero. Sorry. Now, actually, we saw an example of an infinite ring where this is true. Basically, those 2x2 matrices. Here, this shows why the examples of ZM worked, right? Because ZN is a finite ring. Everything, according to this theorem, everything must be either a unit or zero divisor. Now, I want you to pay attention to this because I really didn't word this correctly. My only assumption is that A is a finite ring, right? I didn't say anything about R being commutative or even having an identity, right? I didn't even say this ring has an identity because it turns out that for a finite ring, it is possible for every element to be a zero. And if there is one thing that's not a zero divisor, it must have an identity. Let's see why this is true. Let A be an R and consider just all powers. Set A squared, A cubed, A4, etc. Now, that A squared, A cubed, A4 forever, that is an infinite list, right? I'm listing all the powers back. Agreed? What must be true of this list? What's that now?
They're all in R.
Correct. They're all in R, and R is finite. Can everything in this list be different? No, it can't. Because if everything in this list, A squared, A cubed, if they're all different, that's not possible because there's only finitely many things in R. So is everybody on board with the fact there must be a repetition, right? So there must be, let me write it down here. There must be, actually, I'm going to here. I think plus K4. Like, there's some power that repeats later. And this has to happen at least once. In fact, it has to happen infinitely often, but we don't even need to split those hairs. Everybody okay with that? So this ring is finite. Those powers can't all be different. There has to be a repeat. So I'm going to write this down carefully. So here it says, yeah, I think that's pretty. So where do we go from here? So we have the following equation. Right. And this gives A see if I did that right. Everybody with me up here? Some of you might think I've lost my mind, right? Because look at this. I pulled out AM minus one. Why didn't I pull out all of AM? What would have happened if I pulled out one more power in here? What would I have had here? I'd have to have one, right? And I said there's one there. All right, so that's what I'm trying to skip over. It's going to turn out there is a one, but I'm not assuming that. Everybody okay with that? Now, we now assume A is not a zero divisor. Statement of the theorem says it's going to be either a zero divisor or a unit. So what we're going to do is we're going to show therefore that A is a unit. Okay, well, A is not a zero divisor. Neither is A to the M minus one. It's easy to check this fact because if A to the M minus one hits something and gives you zero, then there's a factor of A in here, and that makes A a zero divisor as well. So if A is not a zero divisor, then neither is power of it. This means, by the previous result, this gives us that A is equal to A to the N minus M plus one. Zero. So A is equal to A N minus now I'm going to use this. I want to identify the identity. Actually, A N minus M. So, notice I didn't assume the identity is there, but I think this thing works as an identity since A is not a zero. Let me prove this. If you look at, actually, I just did this previously too. If you look at this equation, you have the dA minus dA N minus M plus one is equal to zero. That's just multiplying this equation by B, right? Now, putting that B here allows me to pull out an A. So see what I did? I pulled out that A from the other side. Right? So A is not zero divisor. So, B equals B A N minus one, or N minus M. In a similar fashion, I could have multiplied that on the other side by B and gotten AB minus A to the N minus M plus one B is equal to zero, which implies A times B minus A N minus M B equals zero. Therefore, B is equal to A to the N minus M. So A to the N minus M is the identity of R. It exists because for any element of B, it doesn't matter which side you multiply that on, it gives you B back. Therefore, A is a unit. Because the power of A is equal to the identity, so that means that the inverse of A is just one less than it takes there. Here is the final corollary, and I'll talk about what this follows immediately to this last time. Corollary. 9.15. Any, this is a very famous theorem. Any finite integral element. What is a finite integral domain? Finite ring, and it has no non-zero zero divisors. It's a field because any non-zero element has to be. Any questions on that? Yes.
Here, when you have the A equals A to the N minus M plus one, why couldn't you just factor out that additional plus one A plus the other side? See that A is equal
Like here?
to A times A to the N, no, on the other side. You could write the right side as A times A to the N right there, right?
Oh, good to be back.
Right.
Why wouldn't that prove that A to the N minus M is the identity?
Because it only works for A.
Okay, yeah, I was
Earlier,
Oh, yeah.
A as not a zero divisor, we kind of lost its
Oh, at least I'm so alive.
arbitrary.
Right.
Arbitrariness.
Well, it's either a zero divisor. It's the preliminary computations, and it's like, okay,
Pass my own.
if it's zero divisor, we're done. And now we're assuming it's not a zero divisor, and we're showing it's a unit. And along that road, show it's a unit, there has to be an identity.
Yeah.
Does that make sense?
I think so.
This weekend.